Today I have the chance to talk about Gradle meets the mainframe. This is kind of an experience report from what we did at IBM, introducing Gradle as a build system for our purposes, and some specialties, what we need to work around and how to cover a lot of special circumstances here. First of all, I want to introduce myself. My name is Pohl. I'm working for IBM since 2007, and I'm working basically in the System C firmware department. System C is this mainframe. For everybody who not seen this box, I just put a picture here on this slide. Did you get an impression of what this is about? So basically, what I will talk about is the firmware we build with Gradle is part of the system control structure that maintains the system, that operates the system, and give operators a view inside of the system where they can read out sensor data, where they can repair hardware while the system is running, and build up also some higher level assembly instructions used then basically by the operating systems running on top on the system. So just that you get an impression about the context we're talking here. Basically, what I will talk about here is a part of the firmware where we investigated what kind of build system we want to use and want to move forward. We are talking here about one out of roughly 15 subsystems, we call this, which are parts of firmware components running inside of this box. So you need to imagine we have subsystems running firmware on I/O devices, I/O cards, running firmware for the operator consoles, running firmware on the processor chips, and a lot of stuff. This just covers one part, one subsystem, which is called support element, and even there it's only a part of that. But even this small part is roughly 1 million lines of code. And overall, the system has roughly 15 years of history. This means we need to maintain a lot of legacy we have. We need to maintain a lot of functionality we have from the past. Even recently, I modified some header files that were written by my director, basically, which is obviously at least 15 years ago when he touched these files. And in the end, this is also a broad mix of languages. So we have a lot of code written in C, C++, but we are also using Java, some interface definition languages, even proprietary stuff, but also newer age Corba, even if this might appear as an old standard to you. But still it's used here in our cases. We have Perl, Python, and XML stuff, and a lot of things. What I want to draw here on the right-hand side is just a picture of our very initial dependency graph we were able to create. And I can tell you we had some efforts to clean this up from time to time. Usually this happens every couple of years, and then we try to break stuff apart, but over time it gets messed up again. And excuse me. And this time we were thinking of what is a solution to finally start breaking this dependency tree up and end up with a more modularized system and ensure that this is sustained and over the time. And, and therefore we introduced some smart concepts. I will cover very briefly later in this talk, which gets you an idea what we're trying to do so. But we realized that the build system is a very substantial part to achieve this kind of things, and to break stuff apart and to ensure this get not messed up again. So here I want to just give you a brief history of where we're coming from, and this covers just the last roughly 10 years. Before we had other build systems, other approaches, but we started with a proprietary version of scones. This is was the build system when I joined this department, when I joined the firmware. We call this BB scones because BB was an acronym for Böblingen, where we were maintaining a lot of this stuff. we were thinking of how we can get and migrate the system in an evolutionary approach from the old system to a newer one. And there we first introduced a new front end where we're trying to get rid of these old way of build scripts that were mostly generated out of the previous build system definitions, and trying to make it look like sconce, basically. This was a really big effort because we need to support from all the development teams. To this subsystem, there are roughly 50 to 60 developers contributing code regularly, and we're building the entire system every 2 weeks, roughly. So this means the system and the new evolution of the new systems need to be maintained while we're modifying the build system underneath. So this really could only work if we could maintain backward compatibility and could survive while we can always build the entire system. When getting this first step, we were able then, in a big effort, to migrate to a plain sconce version, where we the first time reached again a state where we had a stock build tool, which was much easier to use for especially new people joining this team, and get rid of old artifacts like AFS, which is a shared file system. Probably not everybody knows here, but it's widely used in our area, and get rid of the need of building in a distributed environment, but also be able to build on my local machine, on my local laptop here, which is absolutely feasible in these days. In the former days, it wasn't possible when build took partially maybe a day or even longer. So today, this was really the choice and the path we want to go to. However, we realized that just going to sconce is not the thing we want to go and want to do, because we needed to break up this dependency tree I showed before. And therefore we envisioned a concept of we need to maintain dependencies explicitly. And therefore we thought, let's try to model our pieces of our system and we invented the name part, and that is why we call this thing part build, to restructure our entire system into parts. We thought in the first place to use components, but this term is so overloaded in our cases that we thought this is not a good idea. We need to come up with a new term. That's why I use this part build thing. The basic idea was we want to provide a notion of isolation, and we want to handle dependencies to other parts explicitly. There we borrowed concepts from Maven or Ivy, which already have this kind of system. And the idea was to keep the compatibility to the sconce tree, but also introduce this additional dependency checking, which was a huge step forward. And in the first place, we thought we can just get around with a few parts and just start with big ones. It turned out that this is not true and not feasible for us, because in the end, we ended up with all bigger parts have cyclic dependencies, and we need to break this further apart to get to a directed acyclic graph in the end, to support in the end Ivy and Maven structures here. And in the newer days, particularly beginning of this year, we moved further to Gradle, to bring Gradle into production. We started working on this last year already, but in the end it was this year ready to move this finally into production, and our official build is now using Gradle, even if we have some flaws we need to sort out, basically. And here the idea is again to use the strong dependency mechanics that Gradle provides, and get rid of our own implementation we did on top of sconce, because we thought it's much easier to write extensions for our custom built environments and languages, rather than writing the dependency management on our own. So that's why we choose to pick on Gradle and to get also to a custom stock tool in the end, and benefit also from the ecosystem that's taking part around this. So to give you an idea where we are now, we split this one tree into roughly 1,480 modules. This is what I was saying before. We not ended up with a few big ones, but an endless, very, very small ones to be able to break these cyclic dependencies. Now, one of our next steps is to group them now back again into bigger ones to get rid of all these very, very, very small modules, basically. However, this was a good approach because in that case we now introduced some checkings and some rules to enforce that we cannot introduce new kind of cyclic dependencies between these parts, basically, and to have the ability to express some more, I would call this architectural rules, to ensure that some constraints are implemented in the code base, basically, which wasn't that easy before. We were able, at least in the sconce times, to also use a binary repository like Nexus, where we were publishing all of these few thousand modules into the Nexus and could make use of them later during other build cycles. We never get this fully implemented in where it could be, including all the versioning stuff and things like that, because we decided then first move on to Gradle to get better support here rather than just building everything based on our own implementation here. In the end, we have roughly 10 open source components, where I mean build tools. I mean Java builds, native build. We have Perl, Python stuff here, but we also need to maintain a couple of our own build tools, like Perl is an self-written, maintained IDL language we were using to generate some proprietary inter-process communication, proxy stuff we just need to maintain for also legacy reasons. This was introduced maybe 15 to 20 years before, and it just needs to be maintained also in our code base, basically. And they are quite another, that's why I marked a couple of them blue, because these are very special only things we developed on our own and have in our code base. But we have other things like RPM-based IDL, J for Corba, Java, C++, which is just commonly used also by other projects for sure. From a testing platform, we are now able to build run JUnit tests, and we developed Google tests a lot for running unit tests on C++ basis. For other languages like Python and Perl, we just were using at the moment mainly Google mock hooks, Google test hooks basically, to run these test cases as well. But we are thinking of getting this also integrated in the Gradle build tree to make this more explicit and use the native languages support there in a better way. But that's where we are at the moment. So going from here, I just want to show you now a few examples of what we did so far and what we introduced here with part build, basically. This is a first example of such a part, and there you can see we are still an XML-based approach, which is similar to Maven, where we have in the first place a descriptor, which is group, part ID or artifact ID, you can say, and a version, a description, and a parent, which probably is also known from Maven, where a kind of a template is provided. In that case, we modeled a shared library. Means this is really a C++ shared library. In our case, shared objects. And we borrow a lot of them, and these additional properties will then specify specific things what we are building. We will find a tag section where it will come up, or we get to later. But basically, the library we are building is behind the lib name. This test name was used as a marker in the first place to run automatically then unit tests. The point why we needed to introduce this was also for legacy reasons, because we never had a convention in our library from a directory structure point of view where we could finally rely on whether there are test cases located or not, if they are compatible to unit tests, or if these are special executables built for running manually on the system in the end, or things like that. We hope to improve this over time and introducing additional conventions and working on that. But as you can imagine, getting agreement for when you need to include roughly 50 to 60 developers can be really hard and requires a lot of discussions in the end to get their final decisions, what are the next steps, and to move on here. But this is in the process of working on. The other section you can see here is a dependency description. This is similar to Maven, where we say this shared library depends on other shared libraries. In that case, string conversions, or for test cases, we need to have this make unique package or make unique part, basically. These dependencies can be headers, header-only parts, which describe interfaces, basically, can be shared libraries, but can also be even Java artifacts or other things that are required in our build environment, basically. This you can imagine is kind of the Maven subset we provided, basically. But what's behind it, I want to show you in the next slide probably a little bit more about what specific things we needed to add here to really support C++ and native stuff here in these Maven formats. But because maybe somebody tried already this native plugin for Maven, which is not that good to really rely and build huge projects with. So on this second example, we just have I just wanted to outline basically the specifics we needed to add for C++ things. The funny part for C++, or the important part for C++ is it's not sufficient to just set up a class path as for Java, right? So you cannot rely simply on artifacts on Jar files and put them together in a path. Usually there need to be a lot more specific information available. For example, some specific link flags, some specific symbols, something export, include paths for the headers, and other things that needs to be configured and set up correctly. Even the path or library path needs to be configured for unit tests. And this all needs to work in a transitive manner when working with these huge build trees. And this is what we build basically with these kind of environments and the descriptions. And what we have here, you can see this, we have here this export section, which is basically the stuff we want to propagate in a transitive manner to other parts. If I depend on this particular one, I get all these export sections applied on my specific environment. And on the one hand side, we define some XML tags, which is obvious probably what exactly this is, but in not all cases this was sufficient. That's why we needed to somehow provide additional support for some scripting languages. This is probably where you, or which is one of the statements from Gradle that we say these scripting languages give us the power to gather more flexibility in a build tree rather than using Maven-like builds, right? And this is partially what we introduced here with these scripts. We just said here is an additional script that gets executed automatically for this export stuff, and there have the capability to write some code to add additional stuff to these export sections or to run some checkings on the environment, and depending on what's available there, add additional stuff as well. And this was kind of bridging the gap between a very descriptive model and a more imperative approach to program some additional things here. The same is true for when building this particular piece or this particular part. Even in the build section, we have also the ability to set flags that are only applied during build time, not exported basically. And we have the ability to put here additional scripts. Here you see the tightly coupled definition basically to the sconce system, which we introduced here because we also called the sconce scripts, so we could add additional build scripts for very special purpose cases which are not fit entirely into these library definitions or in these templates we described above here. However, with this approach, we were able to really describe fully our native build and also describe dependencies like this shared library depends on some Java components, which are code generators that needs to be built as well, which then needs to generate some other headers or additional code, which need to be compiled in addition for this thing, and to bridge this gap between languages and dependency things. On the one hand side, on the other hand side, we were able to create a unique, isolated package for C++. The important part here is usually in C++ with these size projects, you have one, for example, include directory, or put root as an include directory and include all the kind of headers. So the dependencies in the headers and in the include sections in the native stuff spread across the entire build tree. And we had no chance to really check this except of changing an include statement and let the compiler figure out if it's still building or not. With this approach, we really forced to have the headers located besides this XML descriptor, making a directory a self-contained descriptor, and we could only get additional stuff by describing them over the dependencies here. And this strong requirement get us into the position that we get a clear understanding which symbols, which include files, which source files belong to a C++ component, and when we are bridging the gap between one component to another one. And therefore we really get now to the state that we have a dependency graph for C++ for components and can work with that now. And the interesting part is we now also got freed up that we no longer really rely on a certain directory structure. We only rely that a certain part follows a certain convention, like putting the right include path, putting the right exports, and can now move these parts along our build tree, basically along our structure, and also be able in general to break out these separate parts and move them to other libraries, basically. However, with the transition to Gradle, we partially lost some capabilities, but not all of them, but that's something I will cover later a little bit more. Basically, when we transitioned from our sconce-based approach to Gradle, we had a long discussion whether we drop all these XML descriptors and going directly to the Gradle model, or whether we should keep them in the first place. And we decided basically to keep these XML descriptors because now we are able to build in the old world with a sconce-based approach, but we are also able to build with Gradle. And to hook this into Gradle was much easier than we thought at the beginning, because we could simply use the settings file to parse all our XML descriptors in our tree, and basically include these projects by simply include one part after the other, setting the project name and the project directory basically from the definitions found in this XML stuff. And later on we decided to simply make these parts list basically available to Gradle in the build in the end as well. And in the build .gradle file in our root project, we simply iterate over this list and set up each part basically. And there we could add now own plugins we wrote. We could add here additional script where we translated our XML descriptors, basically our model, to the thing Gradle needs. So translated to Gradle scripts, into the Gradle model and things like that. This was much easier and very successful in the first place, because this doesn't take us too long to get there, and to keep this backward compatibility was also very beneficial for us. Even though we are realizing at the moment that it is hard to maintain both environments, and we hope we can sort out the latest issues with Gradle soon and then really switch entirely over to Gradle and decide finally in which direction we want to go further then. The advantage of keeping this model, keeping our XML descriptors, were basically we have now support for transitive C++ dependencies in Gradle. The basic Gradle model is not capable of doing so because Gradle at the moment has no descriptors for a native binary artifact so far. But since we have this meta information, we can keep this. Also, adapting stuff when the model or the Gradle statements changing is quite easy because we have only one place where we translate C++ specific stuff into the model. And this is obviously easier than maintaining, in our case, roughly 1,400 build scripts in Gradle, basically. And we discovered now, during the last year, quite a number of incompatible changes in the model where we need to adapt quite some stuff here. So this was basically a good approach. Another advantage here is that the Gradle configuration time is significant when we think about 1,400 projects. The interesting part is due to the fact that we have an old model and can decide in the settings file which of these parts we want to set up as a project in Gradle by limiting this list is quite easy, and we need to calculate our dependency tree anyhow to get the settings and everything right here. So with that, we can, for example, set up just 50 projects for a certain build by limiting the amount by providing some special parameters or projects. We can reduce the configuration time from, for example, 8 seconds to 1 or less than 1 second. However, this is associated with a cost. And at the moment, using the Gradle daemon, we need to parse all our stuff and calculate our own dependency tree roughly 3 seconds to get everything done. However, this is just when calculating everything one by one sequentially. We tried at the moment to parallelize this effort. That's why I grayed this out a little. And here we get to roughly 1 second or 1.5 seconds. So there is quite some room for improvement. And if we still stick to the 8 seconds, we will be much better than paying the cost of 1 second overhead rather than paying the cost of 8 seconds overhead from the Gradle configuration thing. However, we are hoping that this will improve over time anyhow in Gradle, since they are working heavily on the improving performance in a lot of areas. And we will see where we can get there in the end. But for us at the moment, it was very beneficial to keep this approach and to go from there. Another concept I quickly want to introduce here is this dependency checking. This is something in addition we added where we envisioned a concept where everybody can define his own kind of dependency checker. So for example, we have some specific tags. I will come to this in the next slide, basically. And we said we use this tags section or other properties somebody is able to define in the parts, basically. And everybody can hook in via just adding additional dependencies or a dependency checker as a dependency that are used to check basically if a dependency is allowed or not. In Gradle, basically, this looks like I run through my dependency list and combine this with my parent dependencies. I iterate over this list and evaluate for each checker if this, I get the list of checkers, and for each I just call the closure that is underneath that. In Python, we had some Python scripts basically using lambdas there as well and calling these checkers. But in the end, this looks like this basically. So we had in the definitions these tags, for example, and here we distinguished or defined a common or a set of tags. One thing was we said the first one is called common or CAC. This is just a definition of a product thing we have. In the past, we had even more of these tags. For this example, I just picked one with these two, where we say if I have a part that is tagged as a common one, it must not depend on anything else than common. This is the rule here. Or if I have a part tagged as keg, it must only depend on a part that is common or on a part that is keg. And this is strictly enforced by these rules basically here below. The second thing we had here is we need to distinguish between code that goes into the product basically, code that is available as tool, here as a tool, means that it's installed with an additional debug package, so people can use it on the system basically to test some things on their own, but this will never show up in the customer environment. And we have stuff that we tag as none, which is absolutely not part of the product nor the test package. And we have some additional things that is unit test only, which also gets a specific tag. And these rules here were simply checked by you simply querying these lists, giving us the specific set here, and asking then for each dependency, are you contained in this set? And basically we do this only for the direct dependencies. We not check for every part, the entire transitive chain. Because we said if this rule set is consistent for every part, then we should be consistent for everything and not paying the cost of having too much overhead for this dependency checking. And this seems to work out pretty well because now we have we had the ability to start grouping stuff in own segments and have some checking that really enforces us that nobody in the build can break this. And due to the fact that we check this directly after the configuration takes place and the build script is executed as first part of the iteration, we usually run in errors here in maybe 1 or 2 seconds, basically, when we're using the parallel approach or using a subset here. And this is a very powerful tool because now we can introduce dependencies and clean them up also easily, or introduce rules and having the ability to very quickly iterate and check if we get a clean tree afterwards or not. And to really get there, we need to have this clean separation of C++ parts and descriptions, as you can imagine. Another example of this of this checking is an extension here where somebody just said, I just want to tag something in addition. And I write an additional dependency checker to check additional things. And the definition here is simply if a part is tagged as home and implementation, which is home is a bigger component inside of this firmware structure, and says this is an implementation of this component, nobody else, or if it's a home implementation and the other is not a home implementation, this is an error. So I can enforce that nobody depends on my implementation details and only against my interfaces, basically. And this is just a very simple example of these dependency checkers we now introduced. But again, this is very powerful to keep the build tree clean because it's so important to have these architectural rules somewhere formally checked, basically. As I said in the beginning, we tried to clean this up based on paperwork, creating these trees and writing defects on people that should clean up, basically. And this happened at some point, but it's get messed up quickly again. And with that, we have the first time the ability to make build errors out of them. And this is really a big step forward for us. Now I want to show you some other example which we had for scones. We not have this for Gradle yet, but we are looking for getting there. And maybe this is something I want to, or I hope I can save some time for the end to probably open up a discussion on this, basically. What we did is we packaged now every of these parts into an, in the end, tar.gz file. It's just an archive. And declared an IV descriptor where we put in the dependencies to other parts, but have all necessary stuff here modeled inside of this particular piece. Inside of this archive, we have now C++ specific things, basically like we model an include directory which contains basically headers required by others. We have the shared object that is used then by others or needs to be linked against others. We have our Perl XML file to carry this metadata like specific symbols, like specific script definitions. If we had dependencies to like these environment scripts, they would also appear here in this list basically. And we are started to put some RPM specific informations also alongside of this package, because our deliverable in the end is basically RPM. So we decided to just generate some RPM definitions out of the build tree and package everything that's listed there also inside of these packages, that we can use them also to create our production RPMs, our tools RPMs later out of these pre-built packages in the end, to finally hopefully separate the RPM packaging from building these small pieces in the end. However, we know this is not really standard based, and this is why we not try to port this to Gradle. We were started a discussion with the Gradle team whether we can probably work together to get a common definition of these native package, or probably Gradle is getting that far that is developing these kind of definition to somehow model native binary artifacts that can then be stored and versioned in a binary repository or shared across build trees. And I think that will be also the key for really transitive native dependency management. Because other than that, I not really see how this might work in the end. So this is, or covers briefly what we did so far, and at least some concepts which I could present here in 45 minutes. We for sure did some other things, but this will go much further than we have time here. So I want to take the rest of this talk to talk a little bit what we are currently looking at and what we want to go or look at in the future. So at the moment, we are really considering performance things. So at the moment, if a developer develops C++ native code, he needs to run the build system. For Java, it's much easier. I can create with Gradle a Java Eclipse project, an IntelliJ project, and have my compiler in there that compiles instant. For C++, we don't have this because we're based on a Linux environment. We have the GCC toolchain and therefore not having an IDE like Visual Studio, for example. That also gives us, not exactly, but also better turnaround time. So we need to run the build system at the moment. We hope to get to an edit compile loop less than 1 second. Because it's really a pain for every developer, paying maybe 15 seconds or for some really complex stuff a minute to just see that he made some typos in his code. So this is really we want something very strongly looking at and hoping to get there. The other thing is our full build needs to get much faster than it is today. At the moment with Gradle we improved this a lot. With our sconce-based build we were roughly at 40 minutes for our build plus 20 minutes test cases. With Gradle we are at roughly 20 minutes for the entire build tree for compiling and 10 minutes for our test cases. So as you can envision, this is not just unit tests, this is a little bit more here. But we should and really want to get below this magically 10-minute mark. Usually is also documented for continuous integration builds basically to get to this number basically. The other thing we need to look at the moment is to get to a custom Linux build, which is basically currently just happening inside a change root or inside of a Docker image. Therefore, we have some very specific environments where we need to compile our code in. Because it's running in a very specific Linux distribution, we need to maintain to ship this basically with the system, with the mainframe in the end. However, the support for Gradle running in change root is not that great at the moment, or at least there is no concept of doing so. Usually we can run Gradle in a change root for sure, but maybe it would be a good idea to have Gradle know what kind of change root we need and then run inside this change root or run inside a Docker container. Or as an alternative, we probably were also thinking whether we can describe all dependencies to our base system and inside of our base system and probably then resolve them somehow. But this is something we need to figure out. We don't have this yet. We are at the moment just building inside a change root, period. My idea would be really to get some support to make Gradle aware of this and get on supporting Gradle. The other thing is now to, since we have this specific part tree and describe our components separately, we want to break them out into separate repositories that we can maintain them in a more isolated fashion and also on different schedules and not depending so much on our current library as it is today. But I think that we are on a really good track to get there. As a further step, and I think that's where we hopefully can have some time for discussion, is binary representation and publishing of native code. This is something we're really looking for in getting or working there also together with Gradle, probably contributing their code and getting to a clear definition which we can standardize somehow and agree on. And I think this will be then the key to move on here. To finally also get this transitive native dependency, and for us also getting the daemon stabilized, which is really important. We not tried 2.14 yet. We read in the release notes that this is or covers a lot of improvements, but we are not there yet. The other thing is in our build tree, IDE integration at the moment. We had an early look at the build ship, but we are not really sure if this will cover basically all our needs because we have also a large portion of C++ code. And if I got this correctly, the C++ support is there very limited or not existent at all. And Visual Studio support seems to be there, but it's not fully available. So this is something we need to also look at and hopefully get to something where we can provide developers a better experience as they have today, where they need to manually hook this into their favorite IDE and work with to get a very comprehensive setup where Gradle and our build system covers all of the various needs here. Okay, and this basically gets me to the end of my presentation here. And I hope we have still some time for questions or probably a discussion on this binary representation of native thing. Thank you. Yes? No, I think that's achievable. The point is what we tried is, with the approach of how many projects we are setting up, we already tried to extract all information we have out of our meta information. Don't set up any projects in Gradle and directly create a very specific task to invoke the compiler directly. This is a bad shortcut, I know, and we lose dependency checking, but probably this gets us from our edit compile loop really to this less than 1 second. Other questions? Okay. The version conflicts basically we manage in the first place. When we need to resolve our dependency tree entirely, there we need to also maintain or check for version conflicts basically. unfortunately, we not get too far with the implementation and hope that we can basically get this in the Gradle resolving strategy integrated. But therefore, Gradle needs to be aware of native dependencies in another manner than it is today.
Because you need to wrangle recursively,
Right.
in order to be able to deal with that.
Right, absolutely. And unfortunately, this is not, we have not, or are not there yet where we want to be. Okay, then I think we are also over time. So then, thank you again. And yeah.